Okay, here's a quickie to show a simple application of differential forms in physics. There are several ways to prove that a field is conservative. Remember this? One way is to see if the field can be expressed as a gradient of the potential. Okay, is the gravitational field equal to the gradient of the gravitational potential? Okay, the gravitational potential of a point mass is written like this. So capital phi equal to minus g, the big M, little m over r. So this is just a function, so that's a zero form, right? The differential form equivalent of the gradient is taking the exterior derivative of this zero form, and it produces a one form. All right, so here is our zero form. We want to take the exterior derivative, which means we have to take the partial derivative of the zero form in all of the coordinates that we have, ever how many dimensions we have. So we're going to be in spherical coordinates. We have to take it with respect to r, theta, and small phi. So it's got two angles and a radial component. Well, you can see that there is no theta or phi in here, so those just go to zero, and you just get that. That's all right. So what's the partial of that? Well, it's g big M little m over r squared dr. So this is a covector field, a one form. And in vector calculus, you used to sing it like this, that the gravitational force is equal to the gradient of the potential is equal to this times the basis vector, but the ER basis vector and the R hat basis vector are the same. They're both unit vectors. So it looks like this, right? Okay, there's another way. Another way is to prove a field is conservative is if the curl of that field is equal to zero. The curl of the vector field is equal to zero. In differential forms, the equivalent of the curl is taking the exterior derivative twice. So you take the exterior derivative the first time, which we just did, you take it again, right? So here's what we did the first time. So we changed our zero form into a one form by taking the exterior derivative. Now we do it again, okay? But once again, when you take the exterior derivative, you have to take it of the function, in all three coordinates. So you have to take it with respect to r, the theta, and phi. Okay, now you see here immediately dr, wedge dr is 0. And the partial of this with respect to theta is 0. And the partial of this with respect to phi is 0. So everything is 0. So that's just a real simple one that demonstrates how easy these differential forms can do problems. Okay, I'm going to come up with some more challenging ones. I'll see you later.